Welcome to the presentation on Unsplittable Euclidean Capacitated Vehicle Routing. My name is Zhou.
My name is Claire Mathieu.
This is joint work with Fabrizio Grandoni.
Imagine you own a truck delivery company and you must organize the delivery of packages to customers. How would you model this kind of problem?
In this work, we study the Capacitated Vehicle Routing problem, CVRP.
How do you define the CVRP?
We are given a depot O and a set of n terminals. Each terminal has an unsplittable demand in 0, 1. The demand of a terminal cannot be split.
You mean if you need to deliver a package to some address, you are not allowed to open it and split it into several pieces and deliver them separately?
Yes, that's what unsplittable means. There is an unlimited number of identical vehicles. The tour of each vehicle starts at the depot and returns there after visiting terminals of total demand at most 1. 1 represents the capacity of the vehicle. Together, the tours must cover all demands. The objective is to minimize the total length of the tours. For example, in the figure to the left, the blue terminal has demand equal to 0.2. On the figure to the right, the solution consists of 3 tours, red, yellow, and green. You can check that for the red tour, for example, the total demand 0.4, 0.3, 0.2, 0.1 sum to 1, so it does not exceed the capacity. CVRP is fundamental in operations research.
Okay, so now we understand the problem. Wow, that's a lot of references.
Yes, CVRP is a well-studied problem.
What are all these colors?
The color depends on the metric space in which the problem is studied. It has been studied on general metrics, Euclidean plane, planar graphs, trees, graphs of bounded tree widths, graphs of bounded highway dimension, and graphic metrics.
Okay, why are there 2 columns?
Because there are 2 settings, the restricted setting in which all demands are equal, and the general setting in which the demands might be unequal.
So that's more general?
Yes, that's the more general setting. In this work, we consider the setting of unequal demands. Our focus is the CVRP on the Euclidean plane.
Okay, now we understand how this work fits in the general context. So, now that we understand the problem and the context, what is the result?
Our main result is a 2+ϵ approximation for arbitrary demands.
2+ϵ. Is this better than what was known before?
Yes, the previous best approximation algorithm has a ratio of 2.694 due to Frickstad and others.
Okay, so that's better. Could you do even better, or is there a lower bound?
There is a lower bound of 1.5.
So, could you get an approximation that would be between 1.5 and 2, even better?
I don't know.
Okay. How do you go about obtaining a 2+ϵ approximation?
The idea is to cluster the small terminals into groups of total demand roughly epsilon, and then we are in the special case in which all demands are big.
Could you do even better than 1+ϵ? A polynomial time algorithm, perhaps?
No, because the problem is NP-hard.
You said that this holds for unequal demands, but the problem has previously been studied for the special case of equal demands. So how do your results compare to those?
Both our results match the best known approximation factors in the corresponding equal demand settings. Now I'm going to present our result on the Euclidean CVRP for big demands only. Let epsilon be some positive constant. We say that a demand is big if it is at least epsilon and is small otherwise. When all demands are big, it is easy to design a polynomial time exact algorithm if both of the two assumptions hold. First, we assume that there is a constant number of locations. Second, we assume that there is a constant number of distinct demands at each location.
You say it's easy, but how do you do it?
By brute force. Each tool only covers a bounded number of demands at a bounded number of locations, so there are only a bounded number of tool configurations which you can enumerate in polynomial time.
Okay, I understand that when the two assumptions hold, the problem is easy. But how do you achieve both assumptions? So let's see the first assumption, reducing the number of locations. How can we reduce the number of locations?
To reduce the number of locations, there are three steps. In the first step, we reduce the instance to bounded distance, which means that the ratio between the minimum distance to the dipole and the maximum distance to the dipole is greater than epsilon. In the figure, the maximum distance is d, and the minimum distance is at least epsilon d, and all points belong to the gray area.
How can you achieve this bounded distance property?
To achieve the bounded distance property, we use Baker's shifting technique by losing a 1 plus epsilon factor in the approximation.
Okay, so now we can assume bounded distance.
In the second step, we decompose the gray area into a constant number of regions called cells. For example, the green region is a cell. For people familiar with rounding techniques in approximation algorithms, this is standard. In the third step, we move each terminal to the center of the cell.
So this is the green cell of the previous slide. The terminals are the 12 blue dots on the picture, and the center of the cell is the black dot in the picture.
When we do that for every cell, we have reduced the number of locations to a constant. We can show that the total cost of moving the terminals to the centers is negligible.
Okay, I understand that you can now assume that the number of locations is constant. What about the second assumption, that the number of demands is constant?
Now we reduce the number of distinct demands at each location.
We apply the adaptive rounding technique introduced by Fernandez de la Vega and Lugano in the context of designing an approximation scheme for bin packing.
Consider any center. First, we sort all demands at that center in non-decreasing order. These are the 12 black bullets on the top figure. Next, we make groups of equal cardinality. These are the 3 groups, each of 4 bullets. And finally, in each group, we round the demands up to the maximum demand in that group. On the bottom figure, you can see that in each group, the bullets have moved.
But when you increase the demands like this, if you had a solution that was previously within capacity, now maybe it would exceed the capacity. So this would change everything?
It's just like the analysis of bin packing.
Okay, so now we have achieved the two assumptions: a constant number of locations and a constant number of distinct demands at each location.
Now we summarize our algorithm for big demands only. In the first step, we reduce to bounded distance. In the second step, we decompose into cells. In the third step, we move each big terminal to the center of its cell. In the fourth step, we apply the adaptive rounding technique on the demands at each center. And in the last step, we solve the resulting instance in polynomial time. This completes the description of the 1+ϵ approximation for the Euclidean CVRP on big demands only. Until now, we assume all demands are big. Now we move on to our main result on arbitrary demands. Now some demands may be small. Let us step back and think about CVRP in general. There is a simple, well-known algorithm called Iterated tour partitioning, introduced by Fabrizio and Zhou in 1985. Since we will draw some inspiration from their algorithm, first, as a warm-up, let us review how that works. Iterated tour partitioning. The algorithm is very simple. There are 3 steps. First, we compute a TSP tour on all terminals.
Wait, a TSP tour? But it does not respect the capacity constraint.
Yes, in this step, we ignore the tour capacity. Next, we partition the tour into segments, each of total demand at most 1. On the figure, we have partitioned the tour into 3 segments. Each segment has total demand at most 1. Finally, for each segment, we connect its endpoints to the depot by adding the orange connection. In this way, on the figure, we get 3 tours. Each tour is within capacity. In the Euclidean space, it is known that this algorithm is a 2+ϵ approximation when all demands are small, and is a 3+ϵ approximation when the demands are arbitrary.
Okay, so that was iterated tour partitioning.
Now we design a more efficient algorithm for arbitrary demands. There are 2 cases, depending on the number of tours in the optimal solution. The most interesting case is when the optimal solution has sufficiently many tours, which is our focus here. We adapt from our previous algorithm for big demands only. How do we deal with small demands? As before, we decompose the plane into cells. The key is to cluster the small demands of each cell into big demands. At a high level, we group the small terminals that are near one another in the cell into clusters. Our clustering approach is a modified version of the iterated tour partitioning. This slide is the part of the algorithm that will have the most interesting analysis. First, we compute a TSP tour on the small terminals in the cell, not in the whole input, but just in the cell. Next, we partition the tour into segments, each of total demand roughly epsilon. Not segments of demand 1, but segments of demand epsilon. Finally, for each segment, we cluster its terminals into a big terminal and place that big terminal at the center of the cell. To that end, we add orange connections between the endpoints of the segments and the center of the cell, not the depot, but the center of the cell.
Okay, so now all demands are big, but now I have a question. What is the cost of this clustering?
In the next few slides, we analyze the cost of our solution. This is the most technical part of this talk. Let opt denote the cost of an optimal solution to the initial instance. We show in lemma 1 that the cost of our solution within cells is at most 1 plus 2 epsilon times opt. To prove lemma 1, consider any cell. The green curves are the optimal solution within the cell. We include the blue part of the boundary of the cell to make the green curves connected. So we obtain a TSP tool visiting all terminals in the cell. Then we partition the TSP tool into segments of total demand roughly epsilon, and we add the orange connections between the endpoints of the segments and the center of the cell. The overall cost of the green curves over all cells is at the most opt. In each cell, the cost of the blue part is at the most 1.5 times the boundary of the cell by Kap's argument. Since the number of cells is a constant, while the optimal solution has a super-constant number of tools, the overall cost of the blue parts over all cells is at the most epsilon times opt. It remains to analyze the cost of the orange connections. Since each segment of the TSP tool has total demand roughly epsilon, the cost of the orange segments can be bounded in the same way as the cost of moving the big terminals to the centers. So the overall cost of the orange connections is at most epsilon times opt. This concludes the proof of lemma 1. Now I'm going to bound the cost between cells. Let opt prime denote the cost of an optimal solution to the clustered instance. Since the clustered instance consists of big demands only, we apply the previous algorithm to obtain a 1 plus epsilon approximation. So the cost between cells is at most 1 plus epsilon times opt prime. It remains to bound opt prime with respect to opt. To that end, we construct a new optimal solution to the clustered instance as follows. First, we compute a bicriterial solution consisting of a set of tools each of capacity 1 plus epsilon. This can be achieved using the assignment lemma by Becker and Paul. The cost of the bicriterial solution is at the most 1 plus epsilon times opt. In order to make the solution feasible, we remove one cluster from each tool so that the total demand of that tool is within 1. It remains to cover the removed clusters. To that end, we include a TSP tool to connect the removed clusters. Since each cluster is at some center, it suffices for the TSP tool to visit all the centers. Since there is a constant number of centers, and the number of tools in the optimal solution is super-constant, the cost of the TSP tool is negligible. Finally, we apply the iterated tool partitioning on the TSP tool to obtain a set of tools within capacity. The cost of this step is negligible, since only epsilon demand is removed from each tool. Now we showed that the overall cost between cells is at most 1 plus 4 epsilon times opt. Combining lemma 1 and lemma 2, we conclude that the overall cost of our solution is at most 2 plus 6 epsilon times opt. Now we move on to the second case, when the optimal solution has a bounded number of tools. The algorithm for this case is an adaptation of Aurora's algorithm for Euclidean TSP. In the first step, we round down each demand to an integer multiple of 1 over 2n. In the second step, we apply Aurora's algorithm to the rounded instance. The solution to the rounded instance can be transformed into a bicriterial solution to the initial instance, where the total demand of each tool is at most 1.5. In the last step, we split each tool into 2 tools, each within the capacity. Now we analyze the cost of our solution. The second step has cost at most 1 plus epsilon times the optimum cost, according to Aurora. In the third step, the cost is at most doubled. So the overall cost is at most 2 plus 2 epsilon times opt. To conclude, let me recap our results. In this talk, we gave a 2 plus epsilon approximation for arbitrary demands. To solve that problem, We also gave a 1+ϵ approximation for big demands only. Observe that for arbitrary demands, there is a gap between the lower bound of 1.5 and the upper bound of 2+ϵ in approximation.
Coming back to the application to truck delivery, is our algorithm practical? Let's see. Partitioning demands into cells, that is, into geographical areas, that seems natural. Clustering small demands in the same cell into larger demands seems reasonable. Solving the big demand problem by brute force can be replaced by a heuristic that would be faster, or maybe we could use integer programming. So any heuristic to solve as well as we can. And finally, there are several steps where we use Aurora's TSP approximation scheme, and that is not practical, but that part could be replaced also by a heuristic. Altogether, maybe some adaptation of our algorithm might be useful in practice.
That's the end of our talk. Thank you.